In the quiet darkness of a remote desert, a single beam of light escapes the horizon. It is not the rising of a star, nor the trail of a comet, but the awakening of a telescope, turning its massive mirror toward the heavens. For a moment, that glint of light bridges the infinite, from the silent mountains of Earth to the heart of galaxies millions of light-years away. Humanity has always looked upward in search of meaning. Yet, for most of history, what we could see defined what we could believe. The stars appeared eternal, unchanging, a fixed map of creation drawn across the night. But as our eyes evolved from mere lenses of flesh into vast mechanical instruments, the universe itself began to change. Or rather, it revealed what it had always been: alive, violent, and unimaginably vast. For centuries ago, Galileo lifted a small telescope toward Jupiter and discovered moons circling another world, proof that Earth was not the center of creation. Today, from orbiting space observatories and radio dishes anchored to the driest deserts on Earth, our vision extends across the entire electromagnetic spectrum, from invisible radio waves to deadly bursts of gamma radiation. Each wavelength tells a different story. Together, they form a cosmic symphony of light and energy, a story still unfolding. We have learned to see beyond the visible, to peer through dust and gas, and to capture the universe in wavelengths the human eye will never perceive. Through radio telescopes, we have traced the invisible arms of our Milky Way. Through X-rays, we've watched black holes tear matter apart. And in infrared light, we've glimpsed the first galaxies born in the shadow of the Big Bang. But for every new window opened, another mystery emerges. What lies beyond the light we can measure? What cosmic events remain hidden behind the veil of our instruments, or encoded in signals we do not yet understand? The universe, it seems, is not silent. It hums, it pulses, it glows in frequencies that whisper secrets about its birth, its structure, and its fate. And though we have built machines to listen and to see, we are still, in many ways, blind. This story is not just about light, but about how we've learned to chase it. From the first accidental discovery of cosmic radio waves in a New Jersey field, to the powerful observatories perched on Chile's Atacama Desert, to satellites orbiting far beyond Earth's atmosphere, each instrument has brought us closer to understanding the grand design of the cosmos. In this journey, we will follow the trail of light itself, how it travels, how it transforms, and how it reveals the unseen. We will descend into black holes where no light escapes, soar through the clouds of Saturn's moons, and drift through the faint glow left behind by the universe's violent beginning. For as long as we have existed, we've looked at the sky and asked the same question: what is out there? But now, standing at the edge of discovery, in a time when machines see deeper than our imagination can reach, a more haunting question emerges. What is looking back? It began not with a telescope, nor a spacecraft, but with static, a faint, unending hiss whispering through the wires of an antenna. The year was 1931. The place, a quiet field in New Jersey. Carl Jansky, a young engineer working for Bell Telephone Laboratories, was tasked with tracking sources of interference that might disrupt transatlantic radio communication. What he found instead would open an entirely new window into the cosmos. Jansky's antenna was an ungainly contraption, a rotating steel frame balanced on wheels, which he affectionately called his merry-go-round. Day after day, it scanned the skies, listening for unwanted noise. He expected lightning, or perhaps the faint hum of human-made transmissions. But then came a strange signal, a constant, steady hiss that rose and fell not with the weather, but with the turning of the earth. At first, Jansky thought it might be the sun. Yet, as the months passed, he realized something remarkable. The signal didn't follow the sun's path. It followed the stars. Each day, the source of the hiss arrived 4 minutes earlier than the last, just as the constellations do when they rise and set. The noise, Jansky concluded, came not from our world, but from the heart of our galaxy. Without knowing it, Carl Jansky had discovered the Milky Way's voice, the faint radio hum of our cosmic home. The hiss was strongest when the antenna pointed towards Sagittarius, the constellation that hides the bright, dense center of our galaxy. The universe, for the first time, had spoken. The discovery might have changed astronomy overnight, but the world of the 1930s wasn't ready to listen. Bell Labs thanked Jansky and reassigned him to other projects. His cosmic radio waves were filed away as an interesting curiosity, nothing more. For years, no one followed up. The instruments of the time were too crude, the concept too strange. After all, who could imagine that the stars themselves might sing in invisible frequencies? But the idea refused to die. A decade later, a self-taught radio engineer named Grote Reber, working from his backyard in Illinois, decided to build his own radio telescope. Using a parabolic dish he constructed by hand, Reber began mapping the sky at radio wavelengths. Slowly, a new picture emerged, one invisible to every optical telescope on Earth. What Reber revealed was a universe alive with hidden energy. The Milky Way glowed not only with starlight but with radio waves streaming from clouds of hydrogen gas and the remnants of ancient supernovas. The invisible became visible. The cosmos was no longer a silent void. It was a broadcast of creation itself. These early radio pioneers had stumbled upon a new form of astronomy, one that would forever change how humanity perceives the heavens. For centuries, astronomers had relied solely on visible light, the narrow band our eyes could detect. But now the sky had opened wider. Beyond the visible spectrum lay a realm of wavelengths billions of times longer, each carrying a story from the farthest corners of space and time. The first radio maps of the Milky Way showed sprawling tendrils of gas stretching between the stars. What appeared empty through a telescope was, in truth, teeming with structure and energy. Later, as instruments improved, radio astronomers discovered strange and powerful objects. Pulsars, the remnants of dead stars spinning hundreds of times per second, emitting beams of radio light like cosmic lighthouses. And deeper still, they found the whisper of something even more ancient, a faint glow coming from every direction in the sky, uniform and constant. It would take decades to understand that this glow was the dying echo of the Big Bang itself, the afterglow of the universe's birth. All of it began with a sound that no one could explain, the hum of the galaxy recorded on a strip of paper in a New Jersey field. For the first time, we were not just seeing the universe. We were hearing it. When Galileo first turned his telescope toward the heavens, he broke a wall that had confined humanity for millennia. But even with that monumental leap, one barrier remained, the limitation of our own biology. The human eye can perceive only a tiny fraction of all the light in the universe. Between roughly 390 and 750 nanometers lies the visible spectrum, the familiar band of colors we know as violet through red. Yet beyond those borders stretches a vast ocean of electromagnetic energy, invisible but very real. For centuries, that ocean was a mystery. We believed light to be a singular thing, pure and indivisible. It wasn't until the 19th century, with the experiments of physicists like James Clerk Maxwell, that we came to understand light as a wave, one expression among many in the electromagnetic continuum. Light, radio, infrared, X-rays, gamma rays, all were part of the same universal language, differing only by wavelength and energy. The revelation changed everything. Suddenly, the cosmos wasn't just what we could see. It was a hidden tapestry woven across countless frequencies, waiting to be decoded. And with that realization came a challenge: to build instruments capable of extending our vision into the unseen. Radio astronomy had opened the first door. But what about the others? What about the realms of heat and cold, of radiation and invisible light, the worlds that neither telescope nor eye could ever perceive unaided? Infrared light, discovered in 1800 by William Herschel, offered one of the first clues. Herschel, while measuring the temperature of different colors in sunlight, noticed something extraordinary. Just beyond the red end of the spectrum, where no visible light shone, his thermometer continued to rise. Something invisible was carrying heat. He had discovered infrared radiation, the hidden warmth of the universe. For nearly a century, it remained a curiosity. Only with the invention of sensitive detectors in the 20th century did infrared astronomy become possible. Suddenly, the coldest regions of space, dense molecular clouds, dying stars, and even the faint afterglow of galaxies, could be observed. The universe had revealed its shadows. Above the violet end of the spectrum lay another frontier: ultraviolet light, X-rays, and gamma rays. These were the realms of violence, energy released by the hottest, most extreme events in existence. Yet on Earth, they were unreachable. Our atmosphere, protective and life-giving, blocks most high-energy radiation from reaching the surface. It was only by leaving the ground, by launching telescopes into orbit, that we could begin to explore these deadly wavelengths. In 1990, the Hubble Space Telescope became our new set of eyes in space. Its cameras peered deep into the ultraviolet and visible spectrum, capturing breathtaking portraits of distant galaxies and stellar nurseries. Hubble's ultraviolet filters revealed the blazing hearts of galaxies, the regions where new stars burned hot and bright. And what we saw challenged our imagination. Swirling maelstrom of gas, collapsing clouds of hydrogen, and bursts of light from stars so massive they burned out in mere millions of years. But even Hubble could only glimpse a fraction of the full picture. Soon came the Chandra X-ray Observatory, designed to see the universe's high-energy frontier, black holes feeding on matter, supernovae exploding into rings of fire, and the invisible jets that streak from galactic cores at near light speeds. Through Chandra's eyes, the cosmos was a storm of radiation and chaos, a realm of titanic forces shaping galaxies themselves. At the opposite extreme, instruments like the Spitzer Space Telescope and later the Herschel Observatory pushed deeper into the infrared. These telescopes could peer through dust, the opaque curtains that block visible light, and uncover the hidden nurseries of star formation. They revealed that even the darkest corners of the Milky Way were alive with motion. Stars being born, gas clouds colliding, and galaxies glowing softly in wavelengths invisible to us. Every layer of the spectrum told a different story. Where visible light showed the beauty of stars, radio revealed the quiet breath of gas between them. X-rays exposed their violent deaths, and infrared uncovered the seeds of new creation. The universe was no longer a single image. It was a multidimensional symphony of color and energy. By combining these wavelengths, stacking them like notes in a cosmic chord, astronomers began to see the universe as it truly is: a living, dynamic, and interconnected system. What we once thought of as darkness was, in fact, light of another kind. And yet, as we expanded our sight into every corner of the spectrum, one question began to linger. If light is only one form of information, what else might the universe be sending us? What hidden forces or signals lie beyond even our most powerful detectors? To know the cosmos, we must learn not only to see but to listen. Across every wavelength, every vibration, every whisper of radiation that reaches our fragile world. For only then can we begin to understand what the universe has been trying to tell us since the beginning of time. For centuries, the greatest limitation in our quest to see the universe was not distance, it was distortion. No matter how large the telescope, how finely polished the mirror, or how precisely aligned the lenses, every observation from Earth was filtered through the same imperfect lens: our own atmosphere. The air that sustains life blurs the heavens. It bends and scatters light, turning stars into flickering points and transforming distant galaxies into ghostly smears. Astronomers longed to escape this shimmering distortion, to gaze at the cosmos with clarity unspoiled by air or weather. The dream seemed impossible until the dawn of the space age. When rockets first breached Earth's atmosphere in the mid-20th century, the vision of an orbiting observatory moved from imagination into engineering. It began modestly. In 1946, American astronomer Lyman Spitzer proposed the idea of a large telescope above the atmosphere. He argued that such an instrument could revolutionize astronomy by eliminating the blurring effects of air and allowing access to ultraviolet and infrared wavelengths blocked from Earth's surface. It took more than 4 decades, but Spitzer's vision would eventually become reality, in the form of the Hubble Space Telescope. Launched in 1990, Hubble was more than just an instrument. It was a symbol, a technological expression of humanity's desire to transcend our limitations. Orbiting above the atmosphere, 547 kilometers from Earth, Hubble could see the universe with unprecedented clarity. Its first images stunned the world. Brilliant star clusters, glowing nebulae, and the majestic swirl of galaxies suspended in the void. But Hubble's early triumph was nearly overshadowed by failure. Within weeks of deployment, scientists discovered a fatal flaw in its mirror, a microscopic error that caused the telescope's images to blur. The world watched as a multibillion-dollar dream seemed to collapse. Yet in that failure came one of NASA's most defining moments. In 1993, astronauts aboard the Space Shuttle Endeavour performed a daring repair mission, installing corrective optics that restored Hubble's perfect vision. When the first clear images returned, they changed astronomy, and perhaps our collective sense of wonder forever. One of the most famous, the Hubble Deep Field, captured a seemingly empty patch of sky. But in that void, after 10 days of exposure, Hubble revealed over 3,000 galaxies, each one a city of stars billions of light-years away. What had once looked like nothing was, in truth, everything. Hubble's success inspired a new generation of telescopes, each designed to look deeper and differently. Where Hubble captured visible and ultraviolet light, the Chandra X-ray Observatory, launched in 1999, peered into the high-energy universe. It showed us the invisible skeleton of the cosmos: exploding stars, neutron cores, and black holes devouring matter. In X-rays, the Milky Way was not a serene spiral but a roiling sea of violent energy. A year later, NASA launched the Spitzer Space Telescope, an infrared eye capable of seeing through cosmic dust. With it, astronomers pierced the thick clouds of star-forming regions and revealed embryonic suns still wrapped in their birth cocoons. Whole galaxies, once hidden by darkness, emerged glowing in infrared light. Together, these space observatories redefined what it meant to see. Each wavelength offered a different layer of reality, a different truth. When their data were combined, the result was not a single image, but a symphony of understanding. And while orbiting telescopes soared above the atmosphere, Earth itself began to host a new generation of giants, ground-based instruments built in places where the air was thinnest and the skies clearest. In the dry, unbroken silence of Chile's Atacama Desert, telescopes like the Very Large Telescope, VLT, and the Atacama Large Millimeter Array, ALMA, rose from the dust like monuments to curiosity. Here, high above the clouds, astronomers discovered ways to counter the atmosphere's interference itself. Adaptive optics, systems that adjust mirrors hundreds of times per second to counteract air turbulence, allowed ground telescopes to rival Hubble's sharpness. The once impossible clarity of space now shone from the Earth itself. Every advance carried us farther, but also deeper into mystery. As our instruments grew more precise, we began to realize that the universe was not as simple as once believed. Galaxies rotated too quickly. Stars moved as if pulled by an unseen force. Space itself seemed to expand faster than it should. The more we saw, the more we found that our vision revealed shadows as well as light. In chasing clarity, we had uncovered something profound and unsettling. Most of the universe, it turned out, was invisible, not just hidden behind dust or distance, but fundamentally unseen. Dark matter, dark energy. Together, they accounted for over 95% of everything, yet emitted no light at all. Our greatest telescopes had shown us the brilliance of creation. Now, they confronted us with the darkness that lies beneath. And so, humanity's gaze turned outward once more, to seek the unseen forces shaping reality itself, to build instruments capable not only of capturing light, but of sensing the invisible. While optical telescopes revealed the universe in color and light, a quieter revolution was taking shape, one that didn't look at the stars, but listened to them. It was a form of astronomy that relied not on mirrors or lenses, but on antennas and waves, tuned to frequencies far below the threshold of human sight. These were the radio eyes of Earth, instruments that would uncover a cosmos invisible to light but alive with energy. By the mid-20th century, radio astronomy had evolved from a backyard experiment into one of the most powerful tools in science. What began with Carl Jansky's faint hiss from the Milky Way had grown into a global network of enormous dishes, each one sensitive enough to detect whispers from billions of light-years away. Through radio waves, astronomers could explore regions of space that light could never penetrate, clouds of gas, the hearts of galaxies, even the edges of time itself. Unlike light, radio waves can pass through dust and debris, revealing the hidden structures of the cosmos. When the first radio maps of the Milky Way were drawn, they showed vast, glowing tendrils of hydrogen, the raw material of stars. Our galaxy, once thought to be a simple spiral of shining stars, was instead a dynamic ocean of gas and energy. But radio telescopes did more than map the galaxy. They began to uncover its mysteries. In 1967, a young astrophysicist named Jocelyn Bell noticed a strange, rhythmic signal in the data from a radio array at Cambridge. It pulsed with the precision of a clock, once every 1.33 seconds. At first, she and her advisor thought it might be artificial, a signal from extraterrestrials. They jokingly labeled it LGM-1, for little green men. It wasn't aliens. It was something far more extraordinary. The remnant of a massive star that had died in a supernova and collapsed into a sphere no larger than a city, spinning hundreds of times per second. These pulsars, or rapidly rotating neutron stars, were nature's most precise timekeepers, and they emitted powerful radio beams that swept across space like cosmic lighthouses. Through radio waves, astronomers could now study the aftermath of stellar death and the behavior of matter under unimaginable pressure. But that was only the beginning. As the technology advanced, new arrays of dishes were built, enormous networks capable of working together as one. By combining signals from telescopes thousands of kilometers apart, scientists created what is known as interferometry, a technique that allows for resolution sharper than any single telescope could achieve. This method gave rise to facilities like the Very Large Array, VLA, in New Mexico, a field of 27 giant dishes stretching across the desert. When working together, they could resolve details in distant galaxies with astonishing clarity. And when linked with radio observatories across continents, they formed an Earth-sized telescope, capable of seeing as finely as if our planet itself were one vast, turning eye. Through these networks, astronomers began to detect something far more powerful and mysterious: quasars. These were distant objects that blazed with the energy of entire galaxies, yet appeared no larger than a pinpoint. Only later did scientists realize that quasars are powered by supermassive black holes, devouring gas and dust at their centers and unleashing jets of energy that stretch across intergalactic space. The faint hiss Jansky heard in 1931 had led, step by step, to the revelation of the most violent objects in existence. Black holes, once purely theoretical, were now seen not by light but by their radio signatures, immense, spinning engines that warped space itself. Then came a discovery that seemed to reach even further back, to the very beginning. In 1965, radio engineers Arno Penzias and Robert Wilson at Bell Labs noticed a persistent background noise in their antenna. It came from every direction, constant and inescapable. No matter where they pointed the dish, the hiss remained. They had stumbled upon the faint afterglow of creation, the cosmic microwave background radiation, the residual heat from the Big Bang cooled and stretched by billions of years of cosmic expansion. The universe itself was speaking, not in flashes of light, but in a gentle, eternal whisper. Radio astronomy had not only expanded our vision, it had connected us to the very origins of time. The sky, once thought silent, was revealed as a living broadcast of energy, a conversation between stars, galaxies, and the fabric of space itself. From that point on, astronomers understood that to comprehend the cosmos, one must listen as much as see. Every wavelength was a voice in a larger symphony, one that told of creation, destruction, and the endless transformation of matter into light. And in the remote deserts of Chile, on high plateaus where the air is thin and the silence absolute, the next generation of these radio eyes was about to open, a vast network built to hear the universe as never before. There are few places on Earth that feel closer to another world than Chile's Atacama Desert. Stretching across the spine of South America between the Andes Mountains and the Pacific Ocean, it is one of the driest and highest places on the planet. A landscape of rust-colored rock, salt flats, and ancient volcanoes. Some parts of the Atacama have not seen rain for centuries. The air is so thin and still that the horizon seems eternal, and at night, the stars shine with a sharpness that rivals the view from orbit. To most, it is a wasteland. To astronomers, it is a paradise. It was here, on these desolate plateaus, that a new era of observation began. One that would bridge the gap between Earth and the cosmos. The Atacama's silence, dryness, and altitude made it the perfect place to listen to the universe, to see farther and clearer than anywhere else on the planet. At 2,600 meters above sea level, on a mountain called Cerro Paranal, stands one of humanity's greatest observatories, the Very Large Telescope, or VLT. The name sounds almost playful, but its purpose is anything but. The VLT consists of 4 massive telescopes, each with a main mirror 8.2 meters across, along with 4 smaller auxiliary telescopes. Together, they can operate as a single, enormous optical instrument capable of resolving details invisible even to the Hubble Space Telescope. Each night, when the sun sinks beneath the Pacific, the domes of the VLT open like the petals of a giant metal flower. The telescopes awaken, turning toward the heavens in perfect coordination. Their mirrors, made of thin, ultra-polished glass coated in aluminum, are so delicate that even the faintest tremor could distort their shape. To prevent that, each mirror rests on a network of 150 actuators, tiny pistons that adjust its curvature hundreds of times per second, compensating for gravity and temperature. The result is breathtaking precision. Through the VLT's eyes, astronomers have watched stars orbit the invisible black hole at the center of our galaxy, mapped distant supernovae, and glimpsed planets orbiting other suns. Yet the telescope's true genius lies not only in its engineering, but in where it stands. The Atacama's dryness means that almost no water vapor clouds the sky, a crucial advantage. Water vapor absorbs infrared light, making it impossible to study the faint heat signatures of distant stars from most locations on Earth. But here, under the Atacama's unbroken clarity, the universe opens itself completely. And this is only one summit among many. Higher still, nearly 5,000 meters above sea level on the Shujnantar Plateau, rises an even more audacious project, the Atacama Large Millimeter/Submillimeter Array, or ALMA. Unlike optical telescopes, ALMA does not gather visible light. Instead, it detects radio waves with wavelengths less than a millimeter-long signals emitted by the coldest and most ancient objects in space. ALMA is a symphony of 66 giant antennas, each one a gleaming white dish up to 12 meters across. Together, they form a single, colossal instrument. Each dish captures faint radio waves from deep space, and through a process called interferometry, the signals are combined, creating the effect of a telescope 16 kilometers wide. With ALMA, astronomers can peer into regions that no other instrument can see. The dense clouds where new stars and planets are being born. They can watch cosmic dust swirl around young suns, detect the chemical fingerprints of life-forming molecules, and trace the earliest structures of galaxies billions of years away. Every antenna of ALMA is mobile, capable of being repositioned by enormous transporters that crawl slowly across the plateau. In this way, astronomers can zoom in or zoom out, adjusting the resolution like a camera lens. When spread across its widest configuration, ALMA achieves such detail that it could detect a golf ball on the surface of the moon. But beyond its engineering marvels, ALMA represents something deeper, a symbol of global collaboration. Built through a partnership among Europe, North America, and East Asia, it unites hundreds of scientists under one purpose: to listen to the universe's most ancient whispers. And those whispers have already told remarkable stories. In its first years of operation, ALMA revealed the structure of protoplanetary disks, the swirling rings of gas and dust where new worlds are forming. It has traced carbon monoxide across distant galaxies and mapped molecules of water in the clouds surrounding newborn stars. In a few faint signals, it has connected us directly to the chemistry of creation. Standing in the Atacama, the irony is hard to miss. In one of the most lifeless places on Earth, humanity has built the most powerful tools ever designed to search for life beyond it. From here, amid salt and silence, we reach across time, into the hearts of dying stars, the births of galaxies, and perhaps even the echo of our own cosmic origins. Yet, for all its clarity, even the Atacama cannot show us everything. There are still wavelengths too faint, too long, or too strange for our instruments to detect. And so, the next generation of telescopes, both on Earth and in space, are being designed not just to see the universe, but to understand it, to uncover how light, matter, and time themselves began. Because beyond every discovery lies a deeper mystery, one that beckons us farther into the unknown. For all its beauty, the universe is not a calm or gentle place. Behind the tranquil light of stars and the delicate spirals of galaxies lies a realm of unimaginable violence. Explosions that outshine entire galaxies, collisions that warp space-time, and energies so intense they tear atoms apart. It is in these extremes, at the very edges of destruction, that the universe reveals some of its deepest truths. Astronomers learned long ago that light is both a messenger and a witness. Every photon that reaches us has survived a journey across time and catastrophe. Some were born in the hearts of stars. Others were released in the final instant of a dying sun's collapse. In their paths are written the histories of creation and annihilation. The first to unveil this violent side of the cosmos were the detectors not of visible light, but of radiation, X-rays, and gamma rays. These forms of light, invisible to our eyes, can only be observed from space, as Earth's atmosphere absorbs them. When the first X-ray observatories were launched in the 1960s, scientists expected to find a few weak sources, perhaps remnants of supernovae or the faint emission of our sun. Instead, they found a universe ablaze. In every direction, space glittered with bursts of high-energy light. Some were steady and constant. Others flared and vanished in seconds. These were the deaths of stars, supernovae, and the feeding of black holes. They revealed that the cosmos was not static but alive, restless, and filled with forces beyond comprehension. One of the most haunting discoveries came from a class of events known as gamma-ray bursts, GRBs. First detected by military satellites in the late 1960s, they appeared as brief flashes of gamma radiation coming from random directions in space. At first, they were a mystery, possibly nuclear tests, perhaps something stranger. But as more were detected, a pattern emerged. These bursts were not from Earth at all. They were coming from the farthest reaches of the universe. A single gamma-ray burst releases, in a few seconds, more energy than the sun will produce in its entire lifetime. They are thought to occur when massive stars collapse into black holes, or when neutron stars collide. Whatever their cause, they mark the most cataclysmic events since the Big Bang. And yet, through their destruction, they also give birth to new elements, the heavy metals like gold and platinum that would one day form planets and life. Our understanding of these violent events deepened with the launch of telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton. These instruments could observe the invisible fireworks of the universe, the expanding shock waves of supernova remnants, the accretion disks of black holes, and the searing heat of gas trapped in clusters of galaxies. Through their eyes, we learned that even in death, stars continue to shape the cosmos. When a massive star collapses, its explosion enriches space with elements that become the building blocks of planets, oceans, and living beings. In a cosmic sense, we are all made of the ashes of supernovae. But these X-ray and gamma-ray telescopes also revealed something far more unsettling. The universe is stitched together by invisible violence. Entire galaxies are bound not only by gravity but by the radiation and magnetic fields generated in their hearts. Massive black holes, millions or billions of times the mass of the sun, sit at their centers, spinning like cosmic engines. When gas and dust fall into them, They unleash jets of energy that shoot across millions of light-years. These are the quasars and radio galaxies first discovered by radio telescopes. The paradox is staggering. At the heart of every galaxy, including our own, lies a region of perfect darkness, a place where light itself cannot escape, and yet, around that darkness, light is born in its most radiant form. For decades, astronomers could only infer the existence of these black holes through their effects. But now, with networks of radio telescopes like the Event Horizon Telescope (EHT), they have begun to see the unseeable. In 2019, the world witnessed the first image of a black hole's shadow, a glowing ring of light encircling darkness, captured by an array of radio observatories spread across the globe, including ALMA in the Atacama. That image, a circle of fire against the void, was more than a scientific triumph. It was a mirror held up to creation itself. For the first time, humanity had glimpsed the boundary between existence and oblivion, the horizon where time and space collapse. Yet even as we study the universe's violence, we find a strange order within it. The explosions that tear stars apart are also the engines that seed new generations of suns. The collisions that seem to destroy galaxies are the events that shape the structure of the cosmos. Out of chaos comes pattern, and from death, creation. Light, in all its forms, radio, infrared, visible, ultraviolet, X-ray, and gamma, is not merely illumination. It is the universe remembering itself. Every photon carries the echo of a moment when energy transformed, when matter lived and died, when the fabric of reality itself trembled. And though we have learned to measure and interpret that light, we are still left with an ancient, haunting question. If destruction can create beauty, what does that say about the nature of the cosmos and our place within it? For answers, astronomers have turned not only to telescopes and satellites but to the invisible ripples of gravity itself, vibrations that move through the very structure of space and time. And when those waves were first detected, they opened yet another window, one that allowed us to hear the universe's most violent events for the first time. For centuries, we believed the universe spoke only in light. Every discovery, from Galileo's telescope to ALMA's vast antenna arrays, had relied on photons to tell the story of space and time. But in 2015, humanity heard something entirely new. For the first time, the cosmos did not shine. It vibrated. The discovery began deep beneath the quiet hills of Louisiana and Washington state, in two identical observatories separated by nearly 3,000 kilometers. Each facility consisted of two immense tunnels, for kilometers long, arranged in an L shape and lined with mirrors so perfect that they could reflect light for kilometers without distortion. This was LIGO, the Laser Interferometer Gravitational Wave Observatory, a machine built not to see the universe, but to listen to the trembling of spacetime itself. For decades, the idea of gravitational waves had existed only as theory, a prediction made by Albert Einstein in 1916. According to his general theory of relativity, massive objects don't simply sit in space. They warp it. Like stones dropped into a pond, moving masses send ripples through the very fabric of reality. When two black holes collide, or when neutron stars spiral together, those ripples travel outward across the universe, stretching and compressing spacetime as they go. But Einstein himself doubted they would ever be detected. The distortions were far too small, shorter than the width of an atomic nucleus, and the universe far too noisy. To measure them would require precision beyond anything humanity had ever built. And yet, a century later, we did. On September 14, 2015, a faint signal appeared in LIGO's detectors. It lasted less than a fifth of a second, a delicate, rising tone that resembled a chirp. For months, the data were checked, rechecked, and analyzed independently by both observatories. When the results were finally confirmed, the news shook the world of science. The signal had come from two black holes, one about 29 times the mass of the Sun, the other 36, spiraling together and merging over 1 billion years ago. In that instant, 3 suns' worth of mass was converted entirely into energy, released as ripples in spacetime. Those ripples had traveled across the universe, stretching and contracting Earth itself by a fraction of a proton's width. Yet LIGO had felt it. Humanity had heard the universe ring like a bell. It was, as one physicist described, the first sound of the universe. That discovery marked the birth of a new kind of astronomy. No longer were we confined to light. Gravitational wave observatories could sense phenomena that emitted little or no radiation at all: black hole collisions, neutron-star mergers, and perhaps even the echoes of the Big Bang. Within 2 years, a second event confirmed the method's power. In 2017, LIGO and its European counterpart Virgo detected the collision of 2 neutron stars. This time, telescopes around the world were alerted within seconds. For the first time in history, astronomers witnessed a single cosmic event both in gravitational waves and electromagnetic light. Radio telescopes, X-ray satellites, and optical observatories all turned their gaze to the same region of sky, a faint, distant galaxy 130 million light-years away. What they saw was breathtaking. A brilliant flash of light known as a kilonova, the birth cry of a new element. The collision had forged gold, platinum, and other heavy metals, scattering them into space. Every ring, coin, and jewel on Earth, it turned out, was born from an ancient cosmic collision. Gravitational wave astronomy had done more than confirm Einstein's vision. It had given humanity a new sense of perception. Light showed us what the universe looked like. Waves told us what it felt like. And together, they painted a picture of a cosmos more dynamic and interconnected than we had ever imagined. In the years that followed, observatories across the globe in Italy, Japan, and soon in India joined the network. Each detection refined our understanding of the universe's most extreme events. With every chirp, we could measure not just distance or energy, but the very geometry of spacetime itself. The implications were profound. For the first time, scientists could directly test the nature of gravity, not in equations but in vibrations. They could trace the history of cosmic collisions, measure the expansion of the universe in a new way, and even search for signs of exotic objects predicted by theoretical physics, such as primordial black holes or echoes of dark matter. Yet, as with every leap in perception, new mysteries emerged. Some signals didn't match expected patterns. Others hinted at phenomena we couldn't explain: asymmetric mergers, unexpected wave shapes, anomalies in timing that suggested unknown physics at work. Had we truly begun to map the final frontier of energy, or had we merely opened another door into a deeper, stranger reality? What became clear was this: light and gravity together had begun a new era of cosmic exploration. The universe was no longer a silent movie. It was a living orchestra, with every collision, every collapse, every formation of a star adding to its ancient score. And in that orchestra, humanity had finally found its place, not as passive observers, but as listeners and interpreters of a cosmic symphony that has played since time began. Yet for all the power of our instruments, there remains a part of the universe that still refuses to speak. A domain so vast and hidden that no light, no wave, and no signal can reveal it completely. That realm is the darkness between galaxies, the invisible web that binds everything together, the cosmic skeleton upon which all creation rests. If every photon we've ever captured represents the visible story of the cosmos, then what lies beyond that story, in the vast, unlit expanse that neither reflects nor emits light, remains our greatest mystery. For all the telescopes that scan the heavens, for all the wavelengths we can see, hear, and measure, they show us only a fraction of what exists. Everything we know, every planet, star, nebula, and galaxy, makes up less than 5% of the universe. The rest, as far as we can tell, is invisible. About 27% is dark matter, unseen mass that shapes galaxies through gravity but cannot be detected directly. And the remaining 68% is dark energy, a mysterious pressure pushing the universe apart faster and faster. We live in a universe we can barely see. The first hints of dark matter came not from theory, but from motion, the way galaxies spin. In the 1970s, astronomer Vera Rubin was studying the Andromeda galaxy when she noticed something strange. The stars at its outer edges were orbiting far too fast. According to Newtonian physics, they should have been flung into space. Yet they stayed bound. Something unseen was holding them in place, an invisible mass extending far beyond the visible stars. Rubin's discovery was met with skepticism at first, but over the decades, it was confirmed again and again. Galaxy after galaxy showed the same behavior. Stars moving too quickly, gravitationally anchored by something we could not observe. What was this unseen matter? It emitted no light, no radiation, no heat. It did not collide with itself like ordinary atoms, and yet it exerted gravity, shaping the very structure of the cosmos. As our telescopes grew stronger, we began to see the fingerprints of dark matter across the universe. Through a technique called gravitational lensing, astronomers could observe how massive clusters of invisible matter bent the light from galaxies behind them, distorting their shapes like glass. These cosmic lenses revealed vast halos of unseen mass surrounding every galaxy, and an immense web stretching across the cosmos, the cosmic web. Imagine an endless network of filaments, like strands of silk connecting galaxies across billions of light-years. At the intersections of these filaments lie galaxy clusters, cosmic cities formed where gravity pulls matter together. Between them stretch immense voids, where almost nothing exists. This is the true architecture of the universe, and dark matter is its scaffolding. Simulations of this cosmic web, created using powerful supercomputers, show an astonishing pattern. Galaxies don't form randomly. They emerge where invisible rivers of dark matter intersect, drawn in by its gravity. It is this hidden structure that dictates where stars are born, how galaxies evolve, and how the universe itself takes shape. But if dark matter sculpts the universe, dark energy dictates its fate. The story began in 1998, when two teams of astronomers studying distant supernovae discovered that the universe's expansion was accelerating. That defied everything we expected. Gravity should slow expansion over time, not speed it up. Something was counteracting it, an unknown force woven into the fabric of space itself. Einstein had once introduced a concept called the cosmological constant, a kind of built-in energy of space that kept the universe stable, only to later dismiss it as his greatest mistake. Decades after his death, that mistake seemed to have been right all along. Dark energy, whatever it is, acts like a cosmic repulsion, pushing galaxies apart, stretching the fabric of space faster as time goes on. The universe is not just expanding, it is accelerating into an unknown future. But even as we name these forces, we do not understand them. Dark matter could be made of exotic particles, WIMPs, axions, or something beyond the standard model of physics. Dark energy could be a property of spacetime itself, or evidence that our understanding of gravity is incomplete. Each discovery only deepens the mystery. To explore this hidden realm, scientists have launched missions unlike any before. The Euclid Space Telescope, launched by the European Space Agency, now maps billions of galaxies to trace the cosmic web in unprecedented detail. NASA's upcoming Nancy Grace Roman Space Telescope will study the bending of light across vast distances to probe dark energy's fingerprints. Together, they aim to chart the invisible structure of everything, to make the unseen seen. Meanwhile, deep underground and in isolated mountain laboratories, physicists have built detectors capable of sensing the faintest interactions between dark matter and ordinary particles. They wait in silence for a collision that might never come, a single flash that could reveal what the universe is truly made of. And yet, the greatest revelation may not come from detecting dark matter directly, but from realizing what its existence means. It suggests that reality, as we perceive it, is incomplete, that the light we see is only a thin surface layer of a far deeper, hidden cosmos. The stars are merely the frosting on an invisible cake of gravity, matter, and void. Every telescope, every detector, every mathematical model draws us closer to an inevitable truth. The universe is not defined by what we see, but by what we cannot. Still, even the invisible web obeys laws, patterns that connect the cosmic scale to the human one. For just as galaxies form where dark filaments meet, so too does life arise where matter and energy converge in balance. And among all the worlds that orbit the stars, one small planet, covered in oceans and cloud, dares to ask where it all began and whether we are alone within it. For as long as we've looked up, one question has haunted humanity more than any other. Are we alone? It is a question written in every telescope's lens, whispered in every signal from the stars, and reflected in our endless attempt to understand where we came from. From the earliest astronomers to the engineers of today's interstellar probes, the search for life beyond Earth has been both a scientific pursuit and a deeply human longing, a mirror through which we examine our own existence. When Earth was first photographed from space, that fragile blue world suspended in darkness, it changed how we saw ourselves. From the Moon, it was a marble of water and cloud. From Saturn, as captured by Voyager 1 in 1990, it was little more than a pale blue dot, a single pixel against an infinite void. Yet that pixel contained everything. Every story, every dream, every heartbeat that ever was. If life could arise here, on a small planet orbiting an average star, could it not also bloom elsewhere? The search began with what we could imagine. Worlds like ours, bathed in light and warmth. As telescopes improved, we learned that planets are not rare, they are everywhere. In the last 3 decades, astronomers have confirmed the existence of over 5,000 exoplanets, each discovered by measuring tiny dips in starlight as a planet passes in front of its star. Many more await confirmation, and statistical models suggest that in the Milky Way alone, there may be more planets than stars, hundreds of billions of potential homes for life. Yet not all worlds are equal. Life as we know it requires balance. Liquid water, a stable climate, and a sun that neither burns nor freezes its planets. The region where these conditions can exist, the so-called habitable zone, has become our first filter in the cosmic search. Some of these worlds have captured our imagination. Kepler 452b, orbiting a star similar to our Sun, lies just within its habitable zone. TRAPPIST-1, a red dwarf star only 40 light-years away, hosts 7 rocky planets, 3 of which might hold liquid water. These discoveries are not merely astronomical, they are existential. Each new world forces us to confront the possibility that life, once thought unique to Earth, may be a universal phenomenon. But if such worlds exist, how can we know whether they truly live? The key lies in their light. When a planet passes before its star, a small portion of starlight filters through its atmosphere. By analyzing that light, breaking it into a spectrum, astronomers can detect the chemical fingerprints of gases like oxygen, methane, and carbon dioxide. These are the signatures of biology. Even the faintest hint of imbalance among them could be evidence of something breathing, growing, or evolving far away. In the coming decades, telescopes like the James Webb Space Telescope, JWST, and the planned LUVOIR and HabEx missions will search for those fingerprints with unprecedented precision. JWST, already peering into the infrared, has begun detecting water vapor, carbon dioxide, and methane in the atmospheres of distant worlds. The first whisper of habitability may already be hidden in its data. And yet, life may not always look like us or even use the same chemistry. Some worlds may harbor oceans of ammonia or methane instead of water. Others may orbit dim stars, their skies perpetually crimson, or exist as frozen moons around gas giants, warmed not by sunlight but by the gravitational tug of their host planets. In our own solar system, such places exist. Beneath the icy crust of Europa, one of Jupiter's moons, lies a vast ocean kept liquid by tidal forces. Saturn's moon Enceladus erupts with geysers that spray water and organic molecules into space. Even Titan, shrouded in orange haze, has rivers and lakes, not of water, but of methane. These are not barren worlds. They are laboratories of possibility. NASA's Cassini mission, which explored Saturn and its moons from 2004 to 2017, changed how we view such environments. When Cassini flew through Enceladus's plumes, it detected water, carbon-based molecules, and hints of hydrothermal activity. the same combination that gave rise to life in Earth's ancient oceans. Suddenly, the question shifted from could life exist to how could it not? The search for life has therefore become a search for signatures, chemical, geological, or even technological. Projects like SETI, the search for extraterrestrial intelligence, listen to the sky for artificial radio signals, narrowband frequencies that nature seldom produces. For decades, the universe has remained silent, save for the hiss of natural phenomena. Yet once, in 1977, a brief and unexplained burst of radio energy, the wow signal, seemed to suggest otherwise. It lasted only 72 seconds and was never heard again. Was it interference, coincidence, or contact? We may never know. But the fact that we're listening, that we've built machines capable of hearing whispers from across light years, says as much about us as it does about what's out there. Perhaps the universe is full of life, yet separated by distance and time. Or perhaps we are early, the first wave of consciousness to arise in a young cosmos. Either possibility is profound. And so, we continue to search, through light and shadow, silence and signal, hope and mathematics. Because in every glimmer of an exoplanet, in every whisper of radiation from a distant star, there lingers a possibility that the cosmos might be aware of itself, looking back, through eyes not unlike ours. And if one day we detect that signal, a pulse, a pattern, a message written in the static, it will not merely answer a question. It will redefine what it means to be human. Long before we had telescopes or satellites, before we even understood what a star was, the heavens themselves gave us a message, written not in sound or symbols but in color. The northern and southern lights have danced across human history as both wonder and warning. Silent curtains of green, violet, and crimson that shimmer and twist above the poles. For ancient peoples, they were spirits, omens, or the breath of gods. For us, they are something even more profound, a dialogue between Earth and the sun. The auroras are among the most beautiful and mysterious natural spectacles visible from our planet. Yet beneath their shimmering grace lies a story of immense power, the constant, invisible conversation between our world and the cosmic forces that surround it. The sun, that steady beacon of life, is not calm. Its surface boils with magnetic storms, arcs of plasma, and violent eruptions that hurl charged particles into space. These solar winds stream outward at millions of kilometers per hour, shaping the vast bubble known as the heliosphere, the sun's protective envelope that surrounds the solar system. When those streams of particles reach Earth, they encounter the planet's magnetic field, our invisible shield. Most of the solar wind is deflected, sweeping harmlessly around us. But sometimes, when the sun releases a particularly intense burst, a coronal mass ejection, the shield trembles. Charged particles spiral along magnetic lines toward the poles, colliding with molecules in the upper atmosphere. In those collisions, oxygen and nitrogen atoms become excited, releasing energy in the form of light. The result: vast, ghostly waves that ripple across the night sky. Green from oxygen at lower altitudes, red and purple from nitrogen higher up. An atmospheric symphony played by the solar wind upon the strings of Earth's magnetosphere. But this beauty carries danger. The same storms that paint the sky with color can also disrupt the delicate web of technology on which our civilization depends. Satellites can be disabled, communication networks interrupted, power grids overloaded. In 1989, a massive solar storm plunged the entire Canadian province of Quebec into darkness for 9 hours. And in 1859, the Carrington event, the most powerful geomagnetic storm ever recorded, set telegraph lines ablaze and produced auroras visible as far south as the Caribbean. If such an event occurred today, the effects could be catastrophic, not to life but to our interconnected digital world. The aurora, then, is both an art and a warning, a reminder that our planet is not isolated but deeply connected to the restless forces of the sun. Modern instruments now monitor these cosmic tempests with astonishing precision. NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's solar orbiter watched the sun in ultraviolet light, capturing eruptions in real time. Satellites stationed at the Lagrange points, where Earth's gravity balances that of the sun, serve as early warning systems for solar storms. Through them, we can predict when the sky will light up and when danger approaches. But the aurora's mystery extends far beyond the poles. Recent studies using data from satellites like Themis and Cluster have revealed that auroras are not just atmospheric phenomena. They are signatures of vast electromagnetic waves coursing through space. These waves, known as Alphane waves, carry energy from the magnetosphere down into the atmosphere, creating shimmering curtains of light that dance in rhythm with Earth's magnetic heartbeat. Even more intriguingly, similar auroral emissions have been detected on other worlds. Jupiter, Saturn, Uranus, and Neptune all host auroras, some far brighter and more energetic than ours. On Jupiter, for instance, the planet's enormous magnetic field interacts with volcanic particles spewed from its moon Io, creating ultraviolet auroras that encircle its poles like rings of fire. Saturn's auroras pulse with radio energy, while even Mars, with its weak magnetic field, produces localized bursts of light when solar storms strike its thin atmosphere. The aurora, then, is not uniquely terrestrial, it is cosmic. A universal language of light, spoken wherever magnetic fields and charged particles collide. And like all languages, it tells us something fundamental: that the universe is dynamic, connected, and alive. In a sense, each aurora is a message, the sun's way of reminding us that we are part of its vast and volatile domain. The same light that nurtures our planet also threatens it. The same energy that sustains life can also undo it. Perhaps that is why humans have always felt a strange reverence beneath the dancing sky. To stand beneath the aurora is to witness our planet's shield in motion, to see, for a moment, the invisible forces that protect us from cosmic chaos. And in those moments of green and violet shimmer, we catch a glimpse of something ancient and cyclical, the rhythm of energy flowing between star and world, echoing the same processes that occur across galaxies and time. The aurora is, in its essence, a whisper of the universe's balance. Beauty born from violence, order shaped by chaos. And as we learn to read that whisper, to predict and interpret it, we begin to understand something deeper, that Earth is not merely in the cosmos, but of it. Each flare, each storm, each shimmering veil of color is a reminder that our world is not isolated. It is connected to the heartbeat of the stars. Every beam of light that travels through space carries with it a fragment of history, a message from the past written in the language of photons. To look into the night sky is not to see the universe as it is, but as it was. Each star is a time capsule, each galaxy a chronicle millions or even billions of years old. The farther we look, the further back in time we travel. Light, in this sense, is the universe's archive, an endless library of moments, encoded across the spectrum. Every wavelength tells a story, from the fiery birth of stars to the fading glow of galaxies on the edge of time. And it is through light that we have learned almost everything we know about the cosmos. When the first photons of the cosmic microwave background radiation were released, the universe was only 380,000 years old, a fraction of its current age. The cosmos was then a dense plasma of particles, opaque to light. As it expanded and cooled, atoms formed, allowing radiation to travel freely for the first time. Those ancient photons have been journeying ever since, stretched by the universe's expansion into microwave wavelengths. Today, they bathe all of space in a faint afterglow, the oldest light we can detect. Captured by missions like COBE, WMAP, and Planck, this radiation forms a near-perfect snapshot of the infant universe. It shows us not stars or galaxies, but temperature fluctuations, tiny variations in density that would one day grow into cosmic structures. In that faint, static pattern lies the blueprint of everything: the first seeds of galaxies, clusters, and the cosmic web itself. Light records not only beginnings, but transformations. When we study a distant quasar, its light may have traveled for 10 billion years. By the time it reaches us, That quasar may have long vanished, its energy spent, its galaxy evolved. Yet its light endures, a memory that refuses to fade. Even the color of that light tells a story. As the universe expands, distant galaxies appear to recede, and their light is stretched toward longer, redder wavelengths, a phenomenon known as redshift. By measuring how much that light has shifted, astronomers can calculate distance, motion, and age. In this way, light becomes not just a messenger but a ruler and a clock, the metric by which we measure the unfolding of time itself. And so, our greatest telescopes have become archivists, instruments that read light like pages of an ancient manuscript. The James Webb Space Telescope, with its golden mirrors and infrared eyes, now peers deeper than any before it, observing galaxies that formed just a few 100 million years after the Big Bang. The light it captures began its journey long before Earth, the Sun, or even our Milky Way existed. To Webb, the universe is not static, but a living memory unfolding backward through time. Each photon it collects is unimaginably old, older than our planet's rocks or oceans, older than the atoms in our bodies. And yet, when it strikes a detector, it becomes something new. A signal, a piece of data, a revelation. But light is fragile. Across billions of years, it has been bent, scattered, and absorbed by dust and gravity. Some of it is lost forever, swallowed by black holes or stretched beyond detectability. What reaches us is incomplete, fragmented, like torn pages of a cosmic diary. To reconstruct the universe's story, scientists combine light from across the spectrum: radio, infrared, visible, ultraviolet, X-ray, and gamma. Each wavelength reveals a different era, a different aspect of cosmic evolution. Together, they form a mosaic of creation. The Hubble Ultra Deep Field, for example, is one such composite, a single image built from weeks of exposure, revealing thousands of galaxies in what once appeared as empty space. In that tiny patch of sky, we see the rise and fall of entire civilizations of stars. It is a reminder that the cosmos is not empty at all. It is overflowing with memory. And memory, as we know, is fragile not just for the universe, but for us. For centuries, we have looked outward and seen ourselves reflected in the stars. Not physically, but philosophically. The universe remembers through light. Humanity remembers through knowledge. Every observation, every experiment, every story of discovery adds to our collective understanding. In this sense, our telescopes are not just tools, they are extensions of consciousness, devices through which the universe becomes aware of itself. When light from a star reaches an astronomer's eye or a sensor's mirror, something profound happens. Two timelines intersect: the journey of that photon across billions of years, and the brief instant of human perception. In that meeting lies a quiet miracle, the past touching the present, the cosmos witnessing itself through us. It is humbling to realize that even as we study light, we are also part of its story. The photons that left ancient stars now strike our planet, are absorbed by our eyes, our skin, our instruments, converted into thought, warmth, and understanding. In this way, light does not just record the universe. It sustains it. It binds matter to energy, memory to meaning, and history to life. We are both the archivists and the archive. And yet, for all we have learned, there remains one question that no photon can answer, one that lingers in the silence between signals. Why does the universe remember at all? Perhaps the answer lies not in the light we receive, but in the darkness that still conceals its origin, a darkness we are only beginning to understand. There is a boundary to what we can see, a horizon not of distance, but of time. Beyond it, the universe vanishes, not into darkness, but into silence. No light can reach us from before the moment when the cosmos first became transparent. Everything beyond that horizon lies in an era we can only imagine, the time before light itself. We call it the cosmic dawn, the period when the first stars ignited, ending the long darkness that followed the Big Bang. For nearly 400 million years after creation, the universe was filled with hydrogen fog. No stars, no galaxies, only cooling matter and expanding space. Then, gravity began its quiet work. Pockets of gas collapsed under their own weight, heating until nuclear fusion burst forth, and the first stars were born. Those first lights, shining into a sea of darkness, transformed everything. Their radiation reionized the surrounding gas, allowing light to travel freely once more. They marked the beginning of structure, of chemistry, of the long chain of events that would lead, ultimately, to us. Today, even our most advanced telescopes, Hubble, James Webb, and those yet to come, strive to glimpse this moment of first illumination. They collect photons that have been traveling for over 13 billion years, stretched by the universe's expansion until they glow in the faint infrared. Each new image pushes us closer to the edge of knowing, to the final visible frontier. But light itself has limits. Cannot escape black holes. Cannot penetrate the opaque beginning of time. And one day it may fade entirely. Cosmologists predict that the universe's expansion, driven by dark energy, will continue accelerating. Galaxies beyond our local group will drift farther and farther away, their light redshifted until it disappears from view. In trillions of years, the night sky will grow empty. The cosmic archive will close, its pages scattering into the void. Future civilizations, if any remain, may never know that other galaxies existed at all. Even stars are temporary. They will burn their fuel and die. Some will explode in brilliant supernovae. Others will cool into black dwarfs, fading into invisibility. Black holes will evaporate, releasing their energy back into space. In the far future, when the last light has dimmed and the universe has cooled to near absolute zero, time itself may lose meaning. This is the heat death, a final equilibrium where nothing more can happen, and the cosmos rests in perfect, eternal silence. And yet, even in that thought lies a strange comfort. The story of light is also the story of transformation. Every atom of our bodies was forged in stars that once burned and died. Every breath we take, every heartbeat, is powered by energy released when matter meets light. The universe does not end in loss. It ends in continuation, an endless exchange of form and memory. The more we learn, the clearer it becomes that the boundary of knowledge is not a wall, but a mirror. When we reach the edge of what can be seen, we are forced to turn inward, to confront the mystery of why we seek it all. Why, in a universe so vast and ancient, does consciousness exist to witness it? Perhaps the act of observation itself is part of the universe's evolution, a way for reality to become aware of its own existence. When our telescopes open their mirrors to the sky, when our detectors record the faint hum of ancient radiation, when we listen for signals in the cosmic static, we are not separate from the universe's unfolding story. We are its latest expression. And maybe that is what light has been trying to tell us all along, that creation and observation are two sides of the same act, that the cosmos does not merely exist, it remembers, and in remembering, it becomes something greater than matter, gravity, or time. Every photon we catch is a fragment of that memory. Every discovery, every signal, every whisper of radiation adds one more thread to the tapestry. As the light fades, it leaves behind more than absence. It leaves awareness. And in that awareness, the universe endures. The story of astronomy has always been the story of vision, of finding new ways to extend the reach of the human eye. From Galileo's fragile tube of glass to Hubble's mirrored gaze in orbit, each new instrument has transformed not just what we can see, but what we can imagine. And now, as the 21st century unfolds, we stand at the threshold of a revolution unlike any before, one that will let us see the universe in its entirety, from its birth to its unseen future. At the forefront of this new era stands the James Webb Space Telescope, JWST, a golden, segmented eye suspended 1,000,000 miles from Earth at the L2 Lagrange point. Where Hubble captured starlight in the visible and ultraviolet, Webb peers deep into the infrared, where the faintest, oldest galaxies still glow. Its mirrors, 18 hexagonal segments of beryllium coated in gold, unfold in space like the petals of a cosmic flower. With them, Webb collects light that has traveled for more than 13 billion years, revealing galaxies that existed when the universe was still in its infancy. Already, JWST has shattered expectations. It has found galaxies older and brighter than models predicted, star systems forming at impossible speeds, and planets with atmospheric compositions that hint at chemistry both familiar and alien. For the first time, we are not merely seeing the ancient universe. We are witnessing the moment structure itself began. But Webb is only the beginning. On the ground, a new generation of giant telescopes is rising from deserts and mountaintops, each a monument to precision and ambition. In Chile, not far from the Atacama observatories, construction has begun on the extremely large telescope, ELT. A structure so vast that its primary mirror will measure 39 meters across, composed of nearly 800 hexagonal panels working in perfect harmony. It will be able to collect more light than any telescope in history, offering images 16 times sharper than Hubble's. With it, astronomers hope to study the atmospheres of Earth-like planets, observe the first galaxies, and even watch the motions of stars around our galaxy's central black hole in real time. To the north, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will join it, each pushing the limits of adaptive optics, systems that flex and twist their mirrors thousands of times per second to counteract the shimmering distortions of Earth's atmosphere. With these machines, the night sky will no longer be a blur of distance but a living map, detailed and dynamic. Beyond Earth, the dream stretches further still. Concepts like LUVOIR, Large UV Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, envision telescopes so large they will require fleets of spacecraft to assemble them. LUVOIR's proposed 15-meter mirror could directly image Earth-like planets orbiting nearby stars, resolving continents, clouds, and even seasonal changes. HABEX, meanwhile, would deploy a starshade, a massive, flower-shaped screen flying thousands of kilometers ahead of the telescope, to block starlight and reveal the faint glow of orbiting worlds. And still farther ahead, in the decades to come, telescopes may no longer rely on mirrors or lenses at all. Engineers are developing interferometric arrays in space, fleets of satellites working in perfect synchronization to create synthetic apertures thousands of kilometers wide. Others envision gravitational lensing observatories, using distant stars or black holes themselves as cosmic magnifiers to peer into otherwise unreachable corners of the universe. Even the moon, once a distant goal, is now being reconsidered as an observatory platform. Its far side, shielded from Earth's radio noise, offers an ideal location for ultra-sensitive radio telescopes that could listen to the universe's earliest whispers, long before the first stars ignited. Every one of these instruments carries a single, shared purpose: to look further back, to listen more clearly, to understand more completely. Each is a continuation of the same ancient impulse that drove early humans to watch the stars and wonder. Yet as our new eyes prepare to open, something remarkable is happening in the way we see. Artificial intelligence now assists in processing the torrents of data pouring from observatories, not merely identifying objects, but discovering patterns humans might miss. Machine learning algorithms can classify galaxies, detect transient phenomena, and even simulate the unseen, predicting what lies between the limits of our observation. In a sense, our telescopes are no longer tools of humanity, but extensions of it, part of a growing collective intelligence that bridges biology and technology. The universe is not being explored by one species, but by the combined vision of human and machine working together. And this partnership raises profound questions. What happens when an algorithm sees something we cannot? When our machines discover a pattern we do not yet understand? Does that moment belong to us or to the universe itself, finding a new way to know its own structure? One truth endures. Every time we've built a new way of seeing, the universe has responded with surprise. Each telescope, each sensor, each mission reveals not just new facts but new mysteries. The cosmos is not running out of answers, it is constantly writing new questions. The telescopes of tomorrow will not only reveal where we came from, they will show us, perhaps for the first time, how consciousness and matter, observer and observed, are part of the same unfolding pattern. And when those new eyes finally open, and the first data streams arrive from across light years, there will be a familiar silence, the same silence that followed the first radio hiss of Carl Jansky's antenna, or the faint chirp of LIGO's detectors. Then, as always, humanity will listen, and somewhere in that silence, a new story of the cosmos will begin. For all that we have seen, for all the light that has reached our eyes and instruments, the universe remains overwhelmingly silent. Across the radio spectrum, from the low hum of hydrogen to the high-frequency bursts of pulsars, there is no unmistakable signal that says, "We are here." It is a silence that stretches across billions of stars and trillions of worlds, a silence both vast and eloquent. This is the paradox that has haunted science for generations. If the cosmos is as old and as fertile as we believe, filled with countless stars and planets, then where is everyone? This question, first posed by the physicist Enrico Fermi in 1950, became known as the Fermi paradox. If intelligent life is common, the galaxy should be alive with evidence. Yet all our searches, all our signals, all our listening, have returned the same answer. Nothing. It is not that we haven't tried. Since the 1960s, projects like SETI, Search for Extraterrestrial Intelligence, have scanned the skies for narrowband radio emissions, frequencies unlikely to occur naturally. The first experiment, led by Frank Drake, used the Green Bank telescope to listen to nearby sun-like stars. It heard only static, but the effort inspired generations. In 1977, a brief and unexplained burst of radio energy, lasting just 72 seconds, was detected by Ohio State University's Big Ear telescope. The astronomer on duty circled the strange spike on the printout and wrote one word beside it: "Wow." For a moment, it seemed as though we might have heard another civilization calling. Yet the signal never repeated, and despite decades of follow-up, its origin remains a mystery. Since then, our ears have grown sharper. The Allen Telescope Array, the Fast Radio Telescope in China, and networks of radio observatories across the world now monitor the sky continuously. Artificial intelligence sifts through billions of frequencies, filtering out interference, searching for patterns too subtle for humans to detect. Still, the universe remains quiet. But perhaps the silence is not absence. Perhaps it is the wrong question. There are many reasons why we might not hear others. The distances are immense. Radio waves weaken over time, dissolving into cosmic noise. Civilizations may use forms of communication beyond our understanding: neutrinos, quantum entanglement, or signals encoded in gravitational waves. Some may exist on timescales so long or short that we simply miss them. Others may have risen and fallen before Earth was even born. And then there is the possibility, sobering and strangely beautiful, that life is rare, that consciousness itself is a fragile bloom in the vast garden of space, that we are, for now, alone. If that is true, then our silence is not a void, but an opportunity, a pause before the first note of a cosmic symphony yet to be played. It means that we, the listeners, are also the first to speak. Every radio message, every interstellar probe, every beam of information we send into space becomes not just an inquiry, but a declaration. We are part of this universe too. And indeed, we have already begun to speak. In 1974, the Arecibo Observatory broadcast the first deliberate message to the stars. A binary code beamed toward a cluster of stars 25,000 light-years away. It contained the basics of human knowledge: numbers, elements, DNA, and a simple diagram of our solar system. Later, the Voyager 1 and Voyager 2 spacecraft each carried a golden record, a phonograph disc etched with sounds and images of Earth. Music, laughter, greetings in 55 languages. They are now billions of kilometers away, drifting through interstellar space, messages in bottles on a cosmic sea. Someday, perhaps in millennia, perhaps never, those records may be found. Or perhaps they will travel forever, silent witnesses to the brief moment when one small world found the courage to announce itself to the cosmos. The search for others is, in the end, a search for ourselves. When we tune our antennas to the sky, we are also tuning inward, asking why intelligence exists and whether awareness has meaning beyond survival. Are we the universe's way of contemplating itself? Or are we an accident of chemistry, destined to flicker and vanish in an indifferent cosmos? The silence does not answer, yet within it we find purpose. It reminds us that meaning is not given. It is created. That connection, whether between stars or between minds, begins with the act of listening. And maybe, just maybe, the silence is temporary. Somewhere, across the black ocean of space, another civilization might be listening too, wondering, as we do, if they are alone. Perhaps one day, their instruments will detect a faint signal, a narrow band rising above the noise. And in that moment, the universe will no longer be silent. 2 points of light, separated by time and distance, will finally speak. Until then, we listen not just for voices beyond Earth, but for the deeper resonance that binds us all. For in the great silence of the cosmos, every question, every whisper, every beam of light carries the same message: that to exist, to be aware, is already to be part of the conversation. At the end of every journey through the cosmos, there comes a moment of stillness, a pause where discovery turns to reflection, where the questions we've carried become mirrors, showing us what we've become in pursuit of their answers. We began by looking outward, chasing the faintest glimmers of light across the abyss. Yet somehow, every photon we've followed has led us back to ourselves. The universe has always been both infinite and intimate. Each telescope, each experiment, each act of wonder is a dialogue between matter and mind, between a cosmos that creates and the consciousness that tries to understand it. In studying the stars, we have uncovered our own origins. The hydrogen of our blood, the carbon of our bones, the iron in our hearts, all forged in the furnaces of long-dead suns. We are, in the truest sense, the universe made aware of itself. And yet, awareness carries a burden. The deeper we look, the smaller we feel. Galaxies stretch across unimaginable distances. Time flows on scales that make our civilizations seem like brief sparks in the dark. The light we observe tonight may come from stars already extinguished, from worlds that lived and died before our species learned to walk upright. To know this is to confront both wonder and sorrow, a recognition that we are temporary within something eternal. But perhaps that is what gives our existence meaning. For all its grandeur, the universe without observers is silent. A vast stage with no audience, no story. It is consciousness that turns light into meaning, chaos into order, randomness into beauty. When a beam of starlight strikes the mirror of a telescope or the retina of an eye, it completes a journey billions of years long. And in that instant, something extraordinary happens. The universe becomes aware that it has existed. That awareness, fragile, fleeting, yet infinite in implication, is our inheritance. As our technology grows, so does our reach. We now see galaxies at the edge of visibility, hear the gravitational music of colliding black holes, and measure the faint pulse of the universe's first moments. We have mapped the invisible scaffolding of dark matter and felt the tug of dark energy shaping our fate. Yet for all this, the greatest mystery remains not out there, but within: why the universe allows itself to be known at all. Perhaps knowledge is not an accident, but a continuation, a process through which the cosmos explores its own possibilities. Life, intelligence, and curiosity are not exceptions to nature. They are its inevitable expressions. To wonder is to participate in the unfolding of existence itself. And so we keep building new observatories, new equations, new languages for the stars. We send probes into the void, not because we expect an answer, but because asking the question defines who we are. The silence between the stars is not a void to fear, but a canvas upon which meaning is written, one photon, one signal, one thought at a time. The last light of the universe, the final flicker of energy that will outlive galaxies and stars, will not vanish without memory. It will carry with it everything that ever was: the warmth of suns, the echo of collisions, the pattern of atoms that once formed consciousness. Even when the cosmos cools into darkness, its story will endure, encoded in the faint hum of entropy, the whisper that says, I was. And if somewhere, in that distant future, another mind, biological or artificial, human or something yet unimagined, stumbles upon that whisper, it will know that once, long ago, there were beings who looked up, saw light, and tried to understand. In that sense, we are not the end of the story, but its continuation, brief, bright, and utterly miraculous. So when we gaze into the night sky, when we trace the constellations and name the stars, we are not just observing the universe, we are participating in it. Every question, every dream, every act of discovery adds one more spark to the cosmic tapestry.